This is a presentation made at epiSTEME6. The title of the presentation is Using Programming with Rural Children for Learning to Think Mathematically. All the authors are teachers in a couple of rural schools. What we mean by thinking mathematically is as it was envisioned in the NCF 2005, which was for the higher purpose of mathematics, applying mathematics in different situations, encouraging reasoning and logical thinking, visualization, abstraction, and patient problem solving. Of course, in addition to that, all the things that are in the syllabus would need to be covered. We work with two rural schools, Isiamblum School and Udavi School, and the children are from the villages around Auroville. They are, in terms of demographics, they are similar to other rural schools, but the mindset is a holistic development of the child, and they are open to different experimentation. Though we have limitations like connectivity, the school had a computer lab as well as backup. Things have changed since we submitted the paper, and we created something called STEM Land in the meantime. And although we started with scratch to programming, presently the children can even program an Arduino, which is here. So this is an Arduino board, and you can program it with C to do different functions. And that's what the children had done to create a board for STEM Land. We just sort of take a stroll through STEM Land. We have various puzzles and games. We are presently, a lot of children are programming in Alice, as well as they are using Blender to do 3D modeling. Strategy games we use quite a bit, as well as pattern matching games, because these are important components of mathematics. So that's Othello and Bloculus. We also fix things. So the student had fixed this fan with an external thing, and he noticed that the fan was actually lifting a paper up rather than pushing it down. We have a Mindstorm, so the students have been building different Mindstorm robots. This is this group's fifth robot. The first time they built a robot, it took them almost 2 weeks, but now they built this thing within 2 hours. So we also do electronics. We salvage components and we build things, but in this presentation we are not focusing on these aspects. That was Sundar. We also have a 3D printer. This is Vaidegi. So what the children make using Blender, they can actually print out in physical size and get an idea of dimensions and scales and what they are building. This was a bracelet that they had built. As I mentioned, we also fix things, so that's what we are training children in here. This is an example of an Alice program. It's a three-dimensional program that is programmed through JavaScript, and so that's some of the children are working with. And this is Abalone. It's a very good strategy game. So one of the students wanted to give a demo of what he had created. He actually started with just water. This entire world was just water. He created the island, the props, the houses, the people, the main character, of course. And so what he's saying is, I made this. So the person can not only walk around, he can interact with other things, and he can even get on a ship and go around the island. And so he created a dock, a ship, and now the ship goes around the island, and you can see fishes and other boats and so on. This is one of the earlier robots that the children had made. This was in a version of a snake. So what we are looking at is how we can actually program it more rather than like only use it like a remote control. So that's something that they are working on. And this, of course, made in Blender. So how we work is we use the theory of constructionism, which basically builds on the theory of constructivism, that we make our own knowledge by actually saying that when we create something outside of our mind that's often shareable, children construct that idea much better. And the other thing we actively used is the idea of making, tinkering, and engineering. making basically taps into the urge of human beings to create something. Tinkering is you play around with it and you get an experience, sort of, you get an intuition into problem solving. And engineering is extracting these principles from the experience and basically bridging the intuition to learning. So one of the first things that we used this, no, actually it wasn't the first, but one of the things we used it with is, and the work we are presenting is using Scratch too, and what we did with programming and what we think it is possible for other schools to replicate. So the first thing we had to address was this thing of sense of numbers. Actually, majority of the children don't have a very good sense of numbers, and the program we looked at was from the textbook. We got this idea of finding the cube root of a very large number, and we thought this would give children a lot of confidence to. We asked them to create a Scratch program that sort of just calculated the cubes because they weren't getting this technique. So this child I was working with wasn't getting this technique. So I said, okay, why not just create something? I'm just giving a demo of Scratch in the right side, so it has all these controls. This is where the program is sort of built, stuck together, and these are all different, about 8 to 10 different things that categories under which you have various commands that you can use in Scratch. So so of course this is not a very hard problem. You know the answer of this is 94. But for the child this wasn't making sense. So I had initially asked her to build a program which just calculated the cube root using the computer, and she was incrementing by 1. But you can imagine for a number like 94 it takes a fairly long time to get the result. So then I asked her to increment it by tens, and that's sort of what we are seeing here. So when she incremented it by tens, she was able to notice the pattern that 3 cube, 4 cube, 5 cube is what is coming here with the additional 3 zeros. No? So the 60 is the 3 zeros, 216 and the 3 zeros. And so once you cross it, you should stop. So that's the algorithm she used to get it. And as she was building it, she actually understood it herself. And this one generates a random number every time. So in this, again, this is still in the 90s and it's 93. So this helped her actually understand the concept of how this is being done and what is the idea behind it. So she became so good that within 1.5 hours in one class, she basically went ahead and did 50 questions with it and then cross-checked it with the game that she had created. Another thing we had used it for was for understanding the concept of circles. So Scratch is a very simplistic program. It only draws straight lines. So the question was, how do you draw a circle if you only had straight lines? So the children rotated and moved and rotated and moved, and depending on how much they rotated, so the theta, the angle, if it was 60 degrees, they would get a hexagon, right? So if you were getting all kinds of regular polygons, and when they finally made the angle really small and rotate by 1 degree and step 1, they finally got a fairly nice looking circle which they could use. So we used the circle for fractions. We said, okay, for fractions, a circle is a nice thing because it gives you an idea that something is missing. And children were often have the difficulty of adding the numerators with the numerators and denominators with denominators. So we said, okay, now that you understand, and the children were very confident that they completely grasped the idea, I wanted them to sort of have a demonstration that showed that, let's say, to others, or that you have actually got it now. So this is what is being demonstrated, that if you add half plus 1/3, then this should have been much larger than half, but the result you're getting 2 by 5 is you're just counting the two pieces without taking into consideration that the two pieces are not the same size and therefore one is fairly large. So, and then the children went ahead and said, no, no, I also want to show why how it's actually done and why you do equivalent fractions. So here they're showing the 1 by 2 is the same as 3 by 6 and 1 by 3 is the same as 2 by 6. And now that the pieces are all of the same kind, 1 by 6 kind, you can add the 2 pieces to the 3 pieces to get 5 pieces. So this is 5 by 6. So the thing is, once children make a demonstration like this, even though it takes some time, they don't need to revisit the topics that we often would say, ah, now I've got it, but again we end up revisiting it after some time. So the thing of creating a thing helps. But in the last example, I had actually created the core fractions thing. It could be scaled, and you could give it a fraction, it gave a result. So I wanted them to use the function, but I told them that now that you've done that, I want you to break the thing apart and figure out how it works and create a pie chart that you actually want. So this is them figuring out how to use pie charts, and connecting. You not only connect the fractions, you not only connect the hours, you connect it to the fractions, you connect it to the decimals, you connect it to percentages by multiplying by 100. And then you have to also work with angles. Now it was interesting that the child who was working on this was multiplying it by 100 and thought, yeah, that's it. And then when they, instead of multiplying by 360 degrees, multiplied it by 100 and didn't get the entire circle and wondered what was going on. Then figured out, oh, 360, yes, it does matter. So with other things like algebra, in fact, compound and simple interest is basically an algebraic equation. Is that children don't have necessarily an estimate of the fact that one is linear and one is actually a nonlinear curve. So I asked them to plot it, and the visualization of these things gives a very clear picture that the two are significantly different and not just marginally different if you were sticking to the first few years. So the few notes is that when children try to explain procedures step by step through programming. For example, the one x cube, like in the first case when they were taking an x and finding x cube, the idea that x cube is x into x into x becomes actually very explicit, and children would otherwise often confuse between x cube and 3x. And something like in the compound interest, the children can correlate that I'm each time I'm multiplying 1 plus r by 100, right? Each time that's the step, that's the addition that I'm doing to what was already there. So the third year, I mean, basically the principal plus interest, the third year is actually related to principal plus interest of the fifth year, which is generally a gap otherwise if they just think of it in terms of formulas. And something like a very non-linear characteristic in compound interest becomes obvious. Something like data handling, which is there in the seventh grade, can be very rich if you use the computers. And we ask them to plot it and so on. And but first, when we got the average, for example, we had a data and we had an average. We wanted to know if the program we had written for average is correct. So the question was, what is the data that needs to be supplied? So one set of students said, oh, we'll just pick up a question from the book, and the back there is an answer, and we'll use that, and we'll check if we are getting the same result. Another set of students said, hey, what happens if all the data is the same? I mean, this is actually very interesting thinking for them to find out trivial cases that they can use for testing their data, and also get an intuition of what average actually means. And they were when they plotted the data, they could even estimate, but just by looking at the data, what would be the expected average value even before calculating it. So these were interesting things that we observed when we were doing averages. We also noted that the fairly abstract ideas, or I guess higher level ideas like a law of large numbers, because you can deal with very large numbers, which can generate random numbers for you. They started noticing that for a randomly distributed data, if they averaged larger and larger numbers, it was coming close to the average of the two endpoints that they had set. So it's interesting that different aspects can also come forward that is not expected of them to know at that age. So what I would like to mention is about the making, tinkering, engineering. The idea that most students have that they are done with something. I'm finished. And the interesting thing with making, tinkering, with basically they wanted to create some. We had a conversation about moon and Earth, and they wanted to create a model of Earth going around the moon, and they saw the sudden jump, and they were not happy with it. They said, no, we have to keep working further till we perfect it. So this concept of perfecting is, I'm going to skip. So it's me skipping. It's not the computer skipping. But so the idea of perfecting something is actually there when you're creating something, because you don't want, you have a idea of quality of work, and you have an idea that I'm not finished, because otherwise children even during examinations they say I'm finished, and they want to move on. So this helps them stay with the problem so they can actually learn it with some depth. Okay, so there are few things that we would like to demonstrate. And a Makey Makey is a instrument that allows. Can you make the sound come? So he's basically debugging at this point. Yes. So how do you make the sound come? Very good. And not only did they know what they did and they were able to debug, they also had theories on why it works and the explanations on why it is. So they are actually been able to theorize that the Makey Makey is a keyboard, and it responds to something like touch, um, and you can press it too. So the other thing is actually far more impressive than it would be in other places, because you are just we don't wear shoes, so our feet are touching the ground, and oh, when your feet touch the ground. Okay, why don't you sit on a chair and show us? Yeah. Yeah. Okay. And the children went ahead and made a overflow detection system with when yeah. So that's the sound it makes. We also use the Finch along with Scratch. The Finch is a simple robot that allows you to connect it allows you to control individual motors and make a small bird finch like robot move. And this exercise is simple to try to make that ball fall on the ground, and so they're debating on how they can get it done. And there are times when it falls short, and times when it slips away. So in real life you have all these other challenges, and you can just create it by just using a paper ball. So there are more animated discussions on what should be done and what's the right way to go about doing it. Can we also did a trinomial cube? Uh, so trinomial cube is a very nice way of children to learn a fairly complex identity of x plus y plus z whole cube. But one of the students was not getting it, so I asked him to actually create it in Alice. So this is a 3D program called Alice. So the height is x and the rest of it is x plus y plus z square. So it's creating a square using each of these elements. And as he was creating it, and he became more systematic about it, and with the heights and widths and the spacing of each of them, he actually understood what the trinomial cube was telling him. So the difficulties we've encountered is that there is some pushback. Some of the work the work we are asking children to do is sort of open-ended, or doesn't have instructions. So it's a bit of intellectual work. So this, there is a bit of pushback from children because they're not used to it. Um, Also, children prefer doing tinkering, and so from tinkering to engineering, where it needs to be systematic and organized, that's a little bit of an effort for them. So, for example, asking children to make a circle, they can do it by tinkering. But asking them to make a very specific circle, for example, a circle with a radius of 50, that they realize requires more thought and more. It's too much of an effort to do otherwise, or a set of systematic circles, 50 radius, 50, 100, so on. Then they move into engineering and try to estimate what is it that is a relation between my program, what I'm doing, versus with the radius or with the perimeter. The initial projects took quite some time, and but the children didn't forget what they were learning very easily once they did the projects. And the bigger problem was from us, from our side, where initially we were a bit too helpful, and it took us some time to realize that as children struggle, they were actually learning, and we were too keen to teach at those times. What we have in terms of assessments of the projects they have made, the self-assessment and projects that they have made, we have seen that children have very easily been able to adapt to new kinds of hardware, Finch, Makey, Mindstorms, Arduinos, and also adapt to new kinds of softwares they encountered along with it. And the interesting thing would be for children to say, "Oh, this is just like Scratch, only now you need to type in case of C," and so on. And the surveys we did of the children, we could see that there is a certain clear improvement in metacognition, where they are able to say what they can do and what they can't do. They value their work, and they also appreciate the work of others and the complexity it goes into the real world. One child, for example, said that now she realizes how much work goes into making the computer look smart. So, in conclusions, I think programming a computer can help children learn conceptual ideas, and of course they can use things they make for something like rigor. And making project can offer an alternative to examinations being the only way to demonstrate proficiency, and it's they can constantly improve in what they are doing, and we've seen that it can be used meaningfully to support higher orders learning, while addressing even the curricular concepts. And there are a very large number of computer centers across this country, in which some of this research and research in this area is actually severely needed, on how we use it well, and uh, leave it fundamentally with the programming can fundamentally change the relationship between a child and a computer, from being just a user to being a creator, a programmer. And as Seymour Papert said, we must let children program the computer instead of attempting to program the children through computers. Thank you.